Let's go.
Hi, we are TBData2 team, and today we are going to present our deep learning project, which is a classification project with convolutional neural networks. And I'm Shuya.
And I'm Kevin.
And I'm Xiongfeng Wang.
And here is our Medium post page, and please clap for us. Thank you. And we're going to, our presentation today will be in this structure. First, we are going to give some background about the problem and the data set. Then we are going to talk about how we pre-process the data set. After that, we are going to talk about, which is also the very important part in our presentation today, how we use the convolutional neural networks to detect which cassava leaves has disease. And we are going to discuss the performance of different models. After that, we are going to talk about what are some further steps we can take to make our model better. And first, let's talk about why we want to solve this problem. So Cassava, which is a little bit far away from our daily lives, but it is actually a very important food security crop in sub-Saharan Africa. And sometimes many of the leaves got disease, many of the crops got disease, and we want to detect if a crop have disease based on the image of the leaves of the cassava. So that's what our project is based on. And the data set we are working on comes from Kaggle, and it consists of more than 20,000 label images of cassava leaves from Uganda. And here is unlike many of the data we worked before, many of the data set we worked previously were just like numeric data and categorical data. This one, it is image data. So the first, we want to decode the data and we specify 3 channels of images with RGB scale and reshape the data. The second step we took in pre-process is we use the CV2 package to extract the data, transforming it from image to NumPy arrays, which we can base our modeling on. After that, because the images are have too many pixels, so it will be very time consuming for our modeling. So we rescale that into smaller NumPy arrays. After that, because we want to test the robustness of our model, we use some augmentation method on our data. And here is a brief EDA of our data. We can see it's actually pretty imbalanced with 60% of the images labeled as CMD. So that will be something we need to remember during the modeling process. And before we get our hands on some of the deep learning models, we use the logistic regression model as a baseline model. From here, we can find that the accuracy is 0.5, which is not as good as, not as desirable as we have expected. So therefore, it is necessary for us to use deep learning method and convolutional neural networks to solve the problem. Next, Alex and Kevin will talk about how we solve the problem.
Okay, so before we use the TF record to train the model, we actually use the raw images. We just feed in raw images to train the model. But there's a problem with it. So the Colab has a limited RAM, and we cannot just upload the whole data set into it. Instead, we're using around like 2,000 to 5,000 images, which will not collapse the online RAM, but also will allow us to see some traits for different models. So we use the CV2 to transform the images to arrays, and we resize to 224 by 3 just to meet up the requirement for the base model. Also, we applied the pixel normalization and one-hot encoding for the labels. To solve the imbalanced data set problem, we use the strat by k-fold splitting. And we first set up the epochs to be 15, but we will add more with early stopping. And I will talk about that soon. And for the batch size, I start with 16 and increase all the way to 128. We can have even larger batch size because this is a parameter we want to be like generally as bigger as possible. But this depends on the combination power we have. So the first one we try is the ResNet as the base model. So we choose the ResNet 15 over 101 because it has a similar result with less layers. Also, we use the listed additional dense layers with activation function ReLU as the follow-up model. And we added the dropout and some and made the convolution layers trainable because we find when unfreezing it, we have a better result. Also, we are choosing the optimizer from like Atoms or SGDM and more, and we find out actually for all the for all different base model, Atom performs better with beta 1 instead of the momentum for the SGD. We also apply the learning rate schedule for both of them. To keep the result comparable, we use the loss categorical cross entropy and the accuracy as the metric. Also, we apply some data augmentation skills like the image data generation and some other skill like reduce linear rate on plan 2, which decrease the linear rate when it get monitored. Also, the ResNet has the lowest validation accuracy of 0.0662. But VGG would used to be the best one before fine tuning. It shows the validation accuracy of 0.068 after fine tuning. And there's one thing I found really interesting during the best run for the VGG16 with Atom as the optimizer. So as you can see, for the first couple of epochs, it's finding the local minimum, and for around like epoch 5 to 25, it's stuck to the local minimum there. And if we apply the early stopping, we will probably just stop here because we usually set up the stop parameter to be 10, and we will not reach the next step and find the best run. So in the later model, I just delete the early stopping method.
So here is where we kind of diverge in our methods. So I loaded the data using TF record. And then TF record is essentially a memory efficient method to store and load data regardless of format. So you can store raw data, like you can store raw data in TF record. You can also store images as well as text as well. And I basically, a lot of my data loading was inspired by Amy Mi-Hyung Zhang's TF record data loading procedure, which basically involved 3 core steps, which were data parsing, image processing, consolidating the data into a TF data set, which is a unique data structure in TensorFlow, and then data augmentation and shuffling. One issue that I had to really keep tabs on throughout the whole process was ensuring that the images, labels, and file names were kept together throughout the process, especially during shuffling, because that could really serve as a detriment to our overall results. And then I used the 60-30-10 train validation test split. And so more about my DenseNet. I used, of all the DenseNet architectures available on TensorFlow, I utilized DenseNet 169 with pre-trained to ImageNet weights because this was neither the shallowest nor deepest architecture. So I did this with hopes of finding a middle ground in terms of capturing the like the overall complexity of the data without underfitting or overfitting. And then after adopting that base model, I added batch normalization, ReLU, and global average pooling before flattening the data, which then connects to the output layer, which then typically connects to the output layer. But instead, I found I actually received better results after adding 3 additional fully connected layers that connect to the output, which contained 512, 256, and 64 units respectively, each with a dropout of 0.3. And initially, I kind of froze the base model entirely and just trained the fully connected layers. But then I would get really stagnant results, especially with my validation accuracy. So then I made the convolutional layers trainable, just so that the convolutions are able to, further extract some features from our unique images of cassava leaves. And I used Atom with the learning rate schedule as my optimizer, and sparse categorical cross entropy as a loss because my labels were not one hot encoded. And then here in my best model, I receive a validation accuracy of around 0.83, which is well above the baseline, as well as a test of 0.84. And then after a little bit of fine tuning, I increased the test accuracy to 0.85. So yeah, this basically documents my experience using DenseNet. At first, you can really see my struggle where my validation accuracy is kind of constant. Had one fully connected layer, and as well as using like this learning rate. And then over time, I made some other modifications and applied other regularization methods. So here it's like something just like changing the batch size, which then changes the steps per epoch, brings my validation accuracy up a little bit. And then here is just adding dropout layers and whatnot, and batch normalization a little bit more. And then here when I add the last 3 dense layers after the flattening and decrease the learning rate a little bit, it brought up my DenseNet to around here. And I would like to show you something that I did with TensorBoard for my best model. And so here you kind of see the epic learning rate. Despite the fact that I had a schedule, it kind of stuck to my initial learning rate of 5 times 10 to the negative 5th, which is okay, which is actually okay because the model did learn. And then here we have the epic, we have the sparse categorical accuracy and the loss function over time. So here we can kind of see that they both follow like a pretty healthy trend in the fact that they both like are decreasing at pretty similar rates, especially and increasing here, especially during the first 6 to 8 epochs. And then kind of after that, we kind of experience some overfitting. So we see here that the training loss continues to decrease while the validation loss kind of remains constant. And here is actually a better representation of that. We see here we reach our max, and then while the training continues to increase, the validation accuracy like stays the same or even decreases a little bit more. And this is what happens when I fine tune it. So I basically load the weights into from the previous model into another blank model, and then I freeze all the layers before the 3 dense layers that I added as customized addition. And then interestingly, the maximum validation accuracy occurs at 0.8475. So here we can kind of clearly see overfitting because of the way the relationship between the train and validation accuracies and losses. So that's another thing to address. But overall, like fine tuning did increase my validation and training accuracy. So for further steps, at least with as far as it goes with DenseNet, I think we could also take some time to explore the other DenseNet architectures, and also find ways to address data imbalances, such as using a larger batch size, since my batch size is a little bit small at 32. And then also ensuring that data is split with the correct distribution, which is kind of hard to do with TF record, but it's definitely something that we can figure out. And then, just more hyperparameter tuning to prevent overfitting. And then we also came across the issue where the testing accuracy was really low on Kaggle while it was high in Colab. So that's another thing to explore too, and also do a little bit more fine tuning in general. And overall, I think we could also explore the many other neural network architectures in TensorFlow, such as Inception and FissionNet, whatnot, and also compare them to the performance of the networks that we presented to you just now. And so, yeah, that's about it. And thank you from TBData2, and I hope you enjoyed our presentation.
Thank you.